Hi and welcome again to another chemistry lesson, and as I promised, we're looking at acids and the strength of acids, and I was going to show you how you can, without having to remember what are the strong acids, what are the weak acids, I'm going to show you a way of how to determine the strength of an acid just by knowing what causes an acid to be strong or to be a weak acid. Okay, so let's quickly just go through what we said. We said that a strong acid is an acid that completely dissociates. In other words, in the compound bond between the hydrogen and the anion, the hydrogen is donated. Okay, so that was one definition, is donating a hydrogen or increasing the concentration. Sorry, not donating hydrogen, donating a proton. The only way to donate a proton is to donate a hydrogen. It's the only one with a single proton in its nucleus. And then the other definition was to increase the concentration of hydrogen. And in either cases, the point is that we want to break the bond between hydrogen and the anion. Okay, so it's a covalent bond. Hydrogen has the positive charge and the anion has the negative charge. Now, what would make it easier to break that bond? Now, if that bond can be easily broken, it would be a strong acid, because then it's very likely to dissociate into these two ions. Okay, if that bond is difficult to break, then it would be a weaker acid. Now, what are the factors that affect the strength or of a bond? Okay, that would be the electron negativity. Okay. Electron negativity, as you can see, electron negativity just comes up everywhere. Electron negativity and atomic radius. Atomic radius. Okay, in other words, the size of the atom. Okay, so again, we're looking at a bond between hydrogen. So we have a hydrogen molecule that is bonded to some anion. Okay, there's our anion, and what is going to affect the strength of the bond between these two. The stronger the bond is, the more difficult it is for the hydrogen to be donated. Okay, so what affects that strength? Well, by far what affects the strength the most is the atomic radius of the anion. Okay, now the larger this atomic radius is, the easier it is to donate this. In other words, how lower the bond strength is between the two. Now you'll notice here that the atomic radius makes a massive leap from the first line of compounds. And just so you know, where do I get this table? This is just the top right hand table on the periodic table. As you can see there, here are the halogens, oxygen, and all the two negative elements here. Okay, so that's it. But what I want you to notice just here in the atomic radius, you won't have this necessarily on your periodic table, but notice here that going from this group to that group, this group is all of a sudden just double that one size. Okay, not necessarily, it's not 100%, but for example, fluorine has half the atomic radius than chlorine, which means if we had hydrofluoric acid and we had hydrochloric acid, which one would be the strongest one? Well, hydrochloric acid by far, because he is much larger, the size between the anion's atomic radius. Make sense? Oh, that's easy enough. Okay, how about bromine? Okay, bromine would be even stronger. He would be an even stronger acid because his atomic radius is even higher. Iodine would then be the strongest of the halogen halide acids. Okay, so these are called sorry, not halogen halides, hydrogen hydrogen halide acids. Okay, and as a matter of fact, these are actually some of the strongest acids that you get. Okay, we get stuff like super acids. We don't need to know the super acids, but these are some of the strongest acids that we get with hydrogen iodide or hydroiodic acid, hydrobromic acid, and hydrochloric acid. Okay, did you get that? Those names? Let's write them down. Okay, hydroiodic, hydrobromic, okay, and hydrochloric. Chloric acid. Now, hydrofluoric acid is actually a weak acid. Okay, because of the small size of the atom, it is actually a weak acid. Now, the next thing that we're going to look at is the electron negativity. Okay, the greater the electron negativity is, the more it is attracting the polarity of the molecule. In other words, if we consider the electrons floating around in here, if the anion has a very high electron negativity, he attracts the electrons towards himself. So in other words, the electrons floating in here would be closer, or would spend more time near the nucleus of the electron negative element. So what would happen is it would cause this hydrogen to have a partial positive charge. Now, if it has a partial positive charge, it is more easily subtracted from this molecule by other elements that have a negative charge. Does that make sense? So if it has a positive charge, it is being attracted by other elements that have a negative charge, and therefore it's easily taken off of here. Now, we see that fluorine has the highest electron negativity, which means that in a bond between hydrogen and fluorine, the fluorine or the electrons will spend more time near the nucleus of fluorine. But here's the thing, if we consider the size of the atoms, and I don't have it here, but the atomic radius for hydrogen is 25, which is exactly half of fluorine. Okay, so if we draw that, there we have our hydrogen, and then just double the size, double the radius, we have fluorine. Okay, now even though it is attracting the electron so much to himself, because he is so small, even though the electrons are tending here, because he's so small, it's not very far from hydrogen anyway. Okay, that is why it's still a weak acid. But look at chlorine. Chlorine also has a very high electron negativity, and because of the size 100, okay, that makes the radius 4 times the size. Okay, now even though he is attracting it maybe less than fluorine, the attractive force on those electrons are still causing them to be further away from the hydrogen, giving it a partially positive charge and being easily subtracted from this molecule. Okay, does that make sense? So now we can see the electron negativity also has an effect. Now, instead of going up or down, you'll see the atomic radius increases as we go down the table. The electron negativity increases as we go up the table, but by far the atomic radius has a stronger effect. So we would try looking, when we look at the periodic table, as we go down, we would increase in our acid strength. But as we go right, okay, even though you can see as we go right, the atomic radius is increasing to the left. Okay, so as we go right, the atomic radius is decreasing, but it's not increasing by that much. Do you see? These are roughly the same size. Okay, these last ones are roughly the same size. Okay, so the increase in atomic radius is not as large as when we go down. So the effect going left is not so prominent as the effect on the electron negativity going right. Look how the electron negativity is increasing. Okay, almost by a 0.5 every jump. Okay, notice that. So in other words, as we go right into the table, we are increasing in acid strength because our electron negativity is increasing. So let me just give you a typical example. Which one is the stronger acid between hydrogen and oxygen and hydrogen and fluorine? Okay, so hydrogen and oxygen, this would be water. Hydrogen and fluorine, this is just hydrochloric acid. Okay, which one would be the stronger acid? Well, they have roughly the same atomic radius. Oh, there's a slight difference. Okay, but there's quite a big difference in the electronegativity. So in other words, strength of the acids, hydrofluoric acid would be stronger. Okay, between water and in ammonia, which one would be stronger? Well, nitrogen has a smaller electronegativity than oxygen. Okay, between hydrogen and carbon, that's methane, if you refer back to your organic chemistry. Okay, again, the electron negativity. Look once again, the size of the electron, the size of the atom, the atomic radius, is roughly the same. Okay, yes, it is almost up to 70. These two are quite far apart, but so is the electronegativity here. Okay, these two are much closer together, but the electronegativity is quite far apart. Okay, we can do the same with hydrogen, with these next ones. So if we look at hydrochloric acid, okay, yes, hydrochloric acid and hydrogen and sulfur, so H2S, we see once again, yes, that the sulfur is much, it would be a weaker acid. Again, not because of the atomic radius, the atomic radiuses are roughly the same, but rather the electron negativity causes the electrons in this bond to want to be closer to chlorine than it would want to be closer to sulfur in a bond between hydrogen and sulfur and hydrogen and chlorine. Okay, so here we can see these factors and how we can relate the various diatomic. So I've been looking at diatomic acids. Okay, diatomic acids, in other words, di being two, atoms being two atoms that's making the bond to form the acids. Now let me just get to polyatomic acids. Okay, polyatomic acids. Now the polyatomic acids are typically where we have hydrogen plus a polyionic ion. Okay, now you'll recall when we worked with polyatomic ions, we specifically looked at one of the elements in the T41 or T43 table. So let's look at that. Here was the T, there was the 4, and here was the 3. My 3 looks terrible, sorry. This one should look like that. Let's try that better. Okay, Here's the 3. There we go. That looks better. Okay, T43 table. Now, can you recall what that was all about? Yes, these were the bonds between these elements and oxygen, and we saw that we had typically, and I'm only going to look at a few of them, we're not going to look at all of them. For example, chlorine would react with 3 oxygens, okay, and this was called chlorate. Okay, now the moment chlorate, which was 1 negative, okay, would react with or would bond with a hydrogen, this obviously now becomes an acid. Why an acid? Because it has the potential to donate the hydrogen. Now this is called chloric acid. Chloric. So all we do is we take this letter, this compound, and add the ic at the end. Okay, so chloric. So let's look at them again. Now this time what is going to affect the acid strength is actually the number of electron negative elements that's bonding to hydrogen. So look, chlorine is highly electronegative. Okay, it's got a high electronegativity. But the moment chlorine reacts with 1 oxygen, okay, it is the oxygen is also electronegative. So chlorine was attracting some of the electrons from hydrogen. But now if we have 1 other oxygen there, chlorine's desire for electrons are now partially satisfied by this oxygen, so his pull on the hydrogen is not as much. But the moment I put in another one like that, now there's a bigger pull on the on hydrogen. It's still not very strong, they are satisfying it in themselves, but hydrochloric acid already like that is becoming a fairly strong acid. It's still a weak acid, but the strongest of all the acids that we are going to encounter in our studies is perchloric acid. This is called perchloric acid, and sorry, I'm working here in the bottom corner. Perchloric acid is the highest one because these 4 oxygens together, and the chlorine with the electron negativity, and again remember all of these together form quite a large molecule by this stage. Okay, so the atomic radius at this stage is fairly large. All of these factors together cause hydrogen to be very easily abstracted from this molecule. Okay, so I will look at all of these in just a moment, but just to give you an idea of the acid strengths that we have so far, the strongest acid that we are going to encounter is going to be perchloric acid. This is called perchloric acid, and we'll look at the names again. Perchloric acid. Okay, that would be the strongest one. Then we would go to our halogen halides. They would be next up. Hydrogen halides, sorry. So we saw the strongest one was the one with the largest atomic radius. Then we had hydrobromic acid, and then hydrochloric acids. These would be the strongest ones. Okay, but now let's go back to our table. After that, we'll have another polyatomic acid. Okay, that would be quite strong. Okay, and this actually became the definition of strong acids. If we see chlorine, okay, the next relatively large one with a relatively large atomic radius is sulfur. Okay, and its relatively large electron negativity. Okay, but sulfur and hydrogen itself we saw was actually quite a weak, it's fairly a weak acid. It's stronger than water, because of the relationship between the atomic radii, okay, but itself is not a strong acid. But the moment I start adding oxygens, okay, then it starts becoming a stronger acid because of oxygen's large electron negativity. So again, the strongest one here would be if we had 4 of them. So in other words, hydrogen, sulfur, SO4. Now SO4, I just want to show you here, is in our here. Okay, so the sulfur is in the 4, which means he gets the ick that I was talking about here. Okay, so the T stands for 3. So CO3 would be carbonic, NO3 would be nitric, okay, PO4 would be phosphoric, SO4 would be sulfuric. Chlorine is ClO3, so chlorine and 3 oxygens will be chloric, bromine and 3 oxygens would be bromic, and IO 3 oxygens would be ionic. Okay, so SO4 would be the next one. SO4, this would just be, so it's not perchloric or persulfuric like this one, because he is standard at 4 oxygens. So this will be sulfuric acid. Now, sulfuric acid traditionally has been the defining factor of strong acids, and anything higher than this used to be called super acids. But for us, we'll just consider strong acids and weak acids. Now, that one would be the strongest of, or one of the strongest polyatomic acids. Okay, so notice now where I've been getting these polyatomic ions from. I've been looking at this table, this T43 table. There's the T, the 4, and the 3, and I've been going from the right to the left, and at the top of this this table. So I've looked at chlorine with 4 oxygens, which made it perchlorine, and then the sulfate with 4 was just sulfuric, and now phosphor with 4 oxygens would be phosphoric. But as I'm going to here, by the time I get to phosphoric, since I'm moving back, the electronegativity of phosphoric, by the time I get here, it's a weak, they become weaker acids again. Okay, so sulfuric and perchloric acids, they were strong acids. By the time I get here and there, they are going to be weak acids. Next, I would be looking at adding 3 oxygens. But before I do, let me just quickly go and look at the naming structure again. Where am I getting on these names, the names from? So again, in my T43 table, that is, if I find it in the T43 table, it will get the ick at the end. Okay, now the T43 stands for 343, and that will tell me how many oxygens it must have to get the ick. Okay, if it has plus 1 oxygen, I would add a per, the name, and ick at the end. If it has 1 less, then instead of the ick, I would have an os, like sulfurous, chlorous, nitrous. Okay, it would have that at the end. Okay, and if it has 2 less oxygens than the T43 would suggest, then I would add a hypo in the beginning, the name, and the os at the end. Okay, so hypochlorous or hyposulfurous. Okay, that would be how I name it. So let's look at, for example, hydrogen. Hydrogen, and then SO2. Okay, now if we go down here, these ones would be -1, -2, -3. So sulfuric would be -2, which means this one must have 2 hydrogens to satisfy that -2. Anyway, going on from there, SO4, what would this one's name be? Well, let's find S in my T43. Okay, let's use the T43. There's my T, there's my 4, and there's my 3. S is in the 4, which means I need 4 oxygens, but I don't only have 2, which means I've got 2 less. So this would be hyposulfurous acid. Okay, or hyposulfurous. That's probably how you pronounce it. Let's look at another one, like let's do HNO3. What would this one be called? Well, there's my T. N needs 3, and then it just gets the ick. Okay, I have 3, and therefore this is nitric acid. Okay, shall we try another one? How about phosphor, HP, and HPO, let's say 3. So P, you can see, is 1, 2, 3. So this is negative, P is -3. Okay, and hydro, what would this be? Hydrogen, PO3. If we look at P, P finds himself in 4. Okay, and therefore he needs 4 oxygens. He has 1 less than 4, and therefore this one is called phosphorus. There, I'm missing an H. Phosphorus acid. Sorry for that. Okay, but I think you get the idea, and that is why this one is called perchloric acid, because chlorine is in the 3. Therefore he needs 3 oxygens, okay, to get the ick, but he has 4 oxygens, and that is why it's called perchloric acids. Okay, so as we've been adding the 4s, this was perchloric, sulfuric, phosphoric. Okay, this would be N, since he's in the 3, he would be, if we give him 4 oxygens, he would be nitric. So let's add 3s. Then this would be chloric acid. So chloric acid, and then this one will be, it needs 4, so if I only give it 3 oxygens, it would be sulfurous. And then P would be phosphorus. We looked at that one here, a little bit down there. Okay, and then this one would be the next one we consider here. That would be HNO3, is called nitric acid. Now nitric acid is the standard. Anyone from nitric acid upwards would be considered strong acids. Okay, now here's the one anomaly, and this one I couldn't figure out. Nitrogen is, first of all, he's at the top. He's not to the far right. Okay, he does not have a large electron negativity. Well, it's not small, okay, but his electron negativity is smaller than chlorine. Okay, he has 3 oxygens in NO3. Sorry, this is a mess, but you must just try and follow. Chlorine, if it had 3, to me it would suggest that chlorine, or even sulfur, since they have larger atomic radii, and they have larger electron negativities, well, at least chlorine has, I really expected chlorine, or at least chloric acid and sulfurous acid to be stronger than nitric acid. But in fact they're not. I don't know why, I couldn't figure it out. So of all the things I had to remember, this would be the only thing I had to remember. The rest I could figure out, but I'll have to remember that nitric acid is actually a fairly strong acid compared to the rest, and the rest seem to work out. Anything less than that, and we don't need to go through all of that, you can now, based on this, compare anything like if they give you another element or another acid, you can go and compare it to these, and these you could go and figure out and therefore decide whether it's a strong or a weak acid. So this is basically the strong acids and their names that you will have to remember. Maybe a 30-minute video to give you 1, 2, 3, 4, 5, 6 names was unnecessary. But I found it fascinating, and I hope it helped you actually just to understand a little bit what makes an acid a strong acid. How can you determine it without going to and try and remember all of these off by heart? You can go and figure it out. You just need to remember how the naming structure works, and with the T43 table, I think it's fairly easy. Well, thank you for watching. I hope you enjoyed it. I'll see you in the next video.